simple harmonic motion. Back in grade 10, we did something like that. We even did it in degrees. So we started our journey on trigonometry graphed there. Now we know this pattern here as simple harmonic motion. We're not using y's and x's anymore, or we moved to displacement time functions, and now we have our big girls and boy pants on. We're going to label that as x. So let's just go x equals a sine omega t. A is amplitude, and we're going to introduce this omega as our angular velocity. Some people call it angular frequency. That's a whole nother conversation. So we recognise that as simple harmonic motion. Hey, velocity. Let's differentiate that. If we see a velocity time function that looks like anything with a trig in there, then we go, oh, that's simple harmonic motion, no problem. How about acceleration? That omega is going to come out again. And because we are differentiating cos, that's going to be a negative. So if we see a sine or a cos in an acceleration time function, we go, hey, that's simple harmonic motion. Okay, let's look at that and go, oh my gosh, that's just displacement. So acceleration equals, let's forget that that's omega squared for a minute and just go, that's just a number. Here, what we're looking at is the acceleration is the negative, or acting in a negative way to where we're heading, to our displacement, the direction that we're going. So if you think about a pendulum or some sort of spring, you can appreciate that acceleration is always acting against the direction of movement. So this is a fundamental concept of simple harmonic motion, is that acceleration acts against displacement. So if we can get an acceleration displacement function to look like this, we go, hey, it's simple harmonic motion. And that's important. Okay. Let's go with that, with acceleration equals minus omega squared x, displacement. Okay. From our previous work on motion, we know that acceleration is also, there we go. We are going to just treat that like a differential equation. We're wanting to split that dx up to the other side. And we're going to integrate both sides. The integral and the derivative cancel. And remembering that that's just a number. It's a negative number, but it's just a number. So when we integrate it, it's x squared on 2, and we've got to add a constant. Okay, let's get rid of the 2. Multiply everything by 2. A constant times 2 is actually still just a constant, so that's okay. So we need to find the constant, and all we have in our equation is a velocity and a displacement. So we can't really say, well, at time 0, whatever. It doesn't work like that. But we can come back to our displacement time function, because we're familiar with it, and go, hey, it's pretty easy to find where these displacements are 0. So that would get my x to 0. But when x is 0, well, what is my velocity? My velocity could be anything. It could be a slow-moving tide or a fast-moving guitar string. How would I work out my velocity? So let's go the other way and go, well, let's set displacement to be this maximum. What's my velocity when my displacement is a maximum? My velocity is 0. So my velocity is 0 when x equals, again, our x, depending on our function, it could be a small x or a big X. What do we know about this x? Well, what would we call that measurement? Well, I reckon we gave that a name all the way back in grade 10 and said that's the amplitude. Amplitude is A. So when my displacement is at its fullest amplitude A, my velocity is 0. Let's get rid of this diagram. It's done its job. That diagram's really important for you to understand what's going on. Okay, so we now know that velocity is 0 when x is A. So c equals omega squared A squared. So we can say v squared equals, let's factor out our omega. Oh, it looks like a bottom. And that's going to be, let's put the a squared at the front. Oh, does that look familiar? Let's go with green. There we go there. So that's how we get them. And this is fundamental. If we see a velocity displacement function that is basically a negative quadratic, anything with a negative quadratic, we can say, oh my gosh, that's simple harmonic motion. We've already got our A and we've already got our omega, and we can pop it straight into, I'm running out of room, A sine omega t. That omega is that omega, and that A is that A. So we don't really need to do any calculus. We just need to understand that pattern. Okay, there we go. That'll do. I'm undoing stuff that's good. Omega t. There we go. That's where they come from. Really important that you can work with it as well, so make sure you do the questions that I have set.